McCarty. Last week my group worked on the ranking cycle, which is essentially in charge of producing electric power. So just some setup of like everything that we had. This is the entire system setup up here with the voltage and amp meter reading and our load rheostat. With the condenser tower, the boiler is there, the turbine. And then reading, like to get our data, we did have the technologies we had to use right here. Both of these are the water levels. The top one shows the water levels before we started, and then once we ran the entire cycle, it shows the after, and then like these are just like closer up pictures of the load rheostat, voltage and amp meter, and I just got like the steam when I was coming up the connection tower. So my graphs are like, I don't know, stupid crazy. This is just based off the data that we had though, so like, I don't know, I did my best to try to make it work. But what we were looking for is when the ranking cycle actually reached steady state. I don't know guys, this is what I had. But, so like, what I did, I guess notice like a trend of where it did kind of level out, and that was when time was at 1600 seconds. So I don't know, maybe we pressed stop and start wrong, I don't know. So if you go like, yeah, these are ugly, but I mean, it is what it is, right? So things don't work. And so the boiler temperature brace time was like the best looking graph I got. So that's how I guess took 1600 seconds to be like the, I guess the state to evaluate my conditions and stuff at for what I had to find. And so for the data reduction, like in the report that we had to find, I found all these values, like I said, evaluating at 1600 seconds, but then the pressure that I used to go off of for the boiler and everything was like 767. So I interpolated the thermo book between 750 and 800 to get those values, and everything else. The turbine outlet pressure was 25, and I mean 25.6. So I just like let it go to 25, just for easier use on me, and that's how I was able to get the rest of those values. Just like simple interpolations, it was too much, but yeah. And then so like these are more values that I pulled from the tables that I used in interpolation. And just like looking at the data that I did have, our thermal efficiency that we got was 17. I think it was low, like I said, I don't know, I think it was something to do with our data, but it wasn't like a perfect system, so maybe there's like loss of, I don't know, like steam and power like everywhere else. Like while we were running it, we ran for a total of 10 minutes, so 7:14 to 7:24, and then like throughout the process, we did have a preheat that took about 10 to 15 minutes for the system to warm up and before we actually started and recording stuff. So I think that's also probably where, I don't know, some issues came in. And then like while we were running it, we adjusted the load rheostat, which increasing the load increases resistance, which thus increases the current, and then decreases the voltage, and we stayed around 8 volts. Our amp meter was wrong, like on the actual machine, but on the turbine technologies we figured about like 0.7. So we stayed somewhere in there, making sure that the boiler had enough water in it. I think we were supposed to keep it above an inch, and when we ended, we had like 335 milliliters, something like that, for us to end. The efficiency, I think it's too high in my opinion, but this is just based off the values that I got. I also found the mass flow rate of the water, which was about 0.06 kilograms per second. And then finding the heat of the boiler and the work of the turbine. Like I said, I pulled those values from the tables based off of their enthalpies, respectively for each one. I think that should be it. Yeah. So references, me, Google, and the thermodynamics book.